Hello everyone, I am Pravinkumar, graduate student at the Department of Mechanical Engineering, IIT Bombay, India. Today I will be presenting on unit set of three nonlinear layers for the design of tunable nonlinear metamaterials. So we'll look into the outline of the presentation as introduction to nonlinear ultrasonics, motivation towards harmonic scattering, then defining a research problem by defining a unit set. Then we will look into the reviews and results, and then we will look into the conclusion. So introduction to nonlinear ultrasonics. When a monochromatic ultrasonic wave interacts with the early stage damage early stage damage metals, it will generate higher harmonics such as second harmonics, third harmonics, and so on. The amplitudes of these harmonics are correlated by defining a nonlinear parameters such as beta to understand the intensity of these digital damages present inside the metals. So control and used done an experimental study to understand how the nonlinear parameter varies when the number of fatigue cycles of the aluminum is increases. So here we can clearly see the sensitivity of the beta. It increases quadratically as the number of cycle increases. So as the number of fatigue cycle increases in the aluminum, the early stage damages from dislocations try to accumulate to like introduce dislocation substructures, and then they like will be stopped at the grain boundaries, and there will be local plasticity, and there will be presence of the more number of micro cracks and so on. So all these early stage damages are highly sensitive to non-linear ultrasonic technique. Due to that, this non-linear ultrasonics is preferred for early stage damage detection, especially in metals, composites, and so on. So our today's motivation is to understand the harmonic scattering of these non-linear ultrasonic waves. So Tang et al. Discussed the harmonic scattering of this longitudinal monochromatic wave from the nonlinear inclusion. Here they consider a quadratically nonlinear inclusion. Please note that the linear impedance between nonlinear as well as linear or material or matrix are same. So there won't be scattering due to the impedance mismatch. The scattering will be only due to the nonlinear inclusion only. So that results in the scattering of the second harmonics only. So the same formulation is extended by Kube, and he extended for the quadratic as well as cubic nonlinear inclusion, and he studies harmonic scattering of both longitudinal and transverse waves, and for this both the nonlinear inclusions, and he demonstrated the presence of fundamental second harmonics as well as third harmonics scattered harmonic waves. And uh, both discuss the sensitivity of the harmonically scattered waves with respect to scattering angle. For more details, please look into this beautiful article. Kube discussed harmonic scattering very nicely. So in 2017, Wang and Achenbach use a compensatory wave concept to find out the harmonically scattered waves from 1D nonlinear strip or inclusion, which is quadratically nonlinear. And they obtained theoretical solution for forward as well as backscattered harmonically scattered waves. They extended their efforts for the cubically nonlinear inclusion as well, and they validated the theoretical solutions obtained using reciprocity theorem as well as compensatory waves. So their conclusion from these studies is that the forward scattered waves is directly proportional to the width of this nonlinear inclusion, which is A here, and the backscatter wave is like function of trigonometric function. And since it's a function of trigonometric function, amplitude of the backscatter wave. So in some cases, the backscattered wave is present, and in some cases, the backscattered wave is not at all present. So it's highly sensitive. Backscattered waves are highly sensitive to the width of the nonlinear inclusion. Since most of the harmonically scattered waves are inspired or motivated from the nonlinear optical Raman scattered waves, so we can clearly say that there is a high similarity between nonlinear ultrasonics and nonlinear optics. So the main motivation behind the harmonic scattering is the Raman scattering. So where he discussed that the Raman scattering is highly sensitive to the dimension of the scatterer itself. So based on the dimension, different types of scatterings can be observed, and that demonstrated in nonlinear optics that based on the different like positions or the combinations of the dipoles, the harmonically scattered, these are the forward scattered waves and these are the back scattered waves. Based on these different case studies, there will be high intensity of the back scattered wave. Their intensity varies based on this like large stacking of these dipoles. And when they once and one more fourth case, they demonstrated that when there is a phase shift between these dipoles, actually second harmonics generation, which is SHG, gets cancelled out. That means it's a trapping of second harmonics, nonlinear optics. So the objective of today's study is to define a unit cell which can exploit all these different types of harmonically scattered backscattered waves. Can we see them in a nonlinear ultrasonic domain also? So that is demonstrated through today's study. So let's directly jump into the problem formulation. So it's a linear 2D domain in which these three strips nonlinear layers are defined as a unit cell. This is a nonlinear unit cell. The intensity of the first and third layer are same, and the intensity of the central layer is only varying. And the width of all these three layers is the W, and the width of all these three layers are equal, which is W by 3. And the input was considered in this computational study, which is solved using FEM formulation using Thomson multiphysics. The frequency is 2 megahertz, and backscattered waves are captured at sensor S1, and forward scattered waves are captured at S2. Please note that once again, there isn't any linear impedance mismatch between any of the unit cell as well as linear matrix. The intensity of the non-linearity parameter of these three layers is defined like this one, like intensity 1, which is proportional to the non-linear parameters element of the Monaghan model, which is kept constant for both first and third layer. The only intensity of the third layer, second layer, which is the central layer, is varied, which is I2. It is varied by defining a scaling factor, which varies between 0 to 1. That means 0.25, 5, 0.75, and 1. In these steps, the intensity is varied. So the objectives of this study is to exploit the harmonic scattering responses as we change the width of the complete unit cell, as well as the intensity of the central layer, because these are the highly sensitive parameters. So we exploited these parameters. So towards that, when we consider a unit cell of 300 micrometer size, the harmonic response is shown like this one. This is the input fundamental frequency, second harmonics, and so on. These are forward scattered waves captured at sensor S2. These are the back scattered waves captured at S1. So when we zoom at the second harmonics at the 4 megahertz, if we look into the forward scattered waves, as the intensity of the central layer increases from 0 to 1, the intensity of the forward scattered second harmonics increases. So it's an increasing trend. Similarly, backscattered waves, it increases from red to black. So as the intensity increases, this amplitude of the backscattered second harmonics is also increasing. So when we look into the static term around 0, so static of the backscattered is slightly less, but they are almost same, we can say, for both backscattered and forward scattered. When we go around for the second 600 micrometer width here, then the forward scattered here we can clearly see increasing nature of the amplitude of second harmonics with an increasing the intensity of the central layer. But very interesting observation is observed here when it's a backscattered waves. So amplitude of the backscattered waves, it decreases when the intensity of the central layer increases from 0 to 0.5, from red to green. And from green to 1, once again, as the intensity increases from 0.5 to 1, the amplitude of backscattered wave increases from gray to black once again. That means it's a decreasing as well as increasing nature. So it's a like parabolic nature when the intensity is varied, which is very interesting observation. But will the same happen at the static term? No. That static, it is almost same for both backscattered and forward scattered. That means static terms are almost same for both backscattered and forward scattered waves, irrespective of their dimensions as well as the variation in the intensity, irrespective of their dimensions and the variation of the intensities. Now, when we go around for the 900 micrometer case study, one more interesting thing is observed. we know that as intensity increases, the amplitude of second harmonics of forward scattered wave increases. But if we look into the amplitudes of the backscattered waves, as the intensity increases from red to black, it decreases in which is completely opposite to the observations which we had made, which is particular to this dimension, is 900 micrometer, and which is very interesting result. So using these results, we can manipulate nonlinear waves, and the static terms are almost same. And one more very interesting result is for at 2100, where you can clearly see that there isn't second harmonics present at all. And as the dimension is increased, the third harmonics pops up along with the second harmonics for forward scattered wave. The forward scattered waves, the intensity increases. As the intensity increases, their amplitude increases. But here the backscattered waves, the second harmonics is not at all present, third harmonics is also not present. But static term is still present. So in conclusion, the review of all backscattered waves, the complete variation of the amplitudes as the intensity of the center layer is varying is seen here. Like at 600, it decreases, increases, as well as increases. At around 1200, it decreases, and as we had seen at 2100, there isn't second harmonics present at all for backscattered waves. And we are once again saying that as demonstrated by harmonic scattering study, it is sensitive to the wavelengths also, their intensities and how their amplitudes are. So coming back to our motivation. So did we validated all different types of results? Yes, we seen these different types of results and exactly similar responses in the non-linear ultrasonic domain also, including scrapping of this one. So in conclusion, a unique nonlinear unit cell is proposed. Backscatter harmonic waves are highly sensitive to dimension as well as intensity, whereas forward scatter waves are directly proportional to the dimension as well as intensity. We had seen the topping of second harmonics of the backscattered harmonic waves. And in future, we will be using an inverse design approach and considering clusters of unit cells to design a novel nonlinear metamaterials to control nonlinear ultrasonic waves. Please give your feedback by scanning this one or by visiting this link. Thank you for your valuable time.